doing side projects and stuff. But yeah, I just kind of randomly found this group. I'm in a few member of a few like Bay Area functional programming meetups that I kind of joined in the pandemic and didn't really like right first timings. I never got to go to any of them in person, but yeah, excited to meet you guys and yeah, and the book looks really interesting too. So just started skimming it. So
yeah. Yeah, if you wanted to do a deep dive into the logic behind some of the structures that functional programmers use, this is the book.
yeah, yeah, it looks really good. Yeah, so
Yes.
coming up to speed in some of the notation, I guess like I hadn't seen like the boldface semicolon stuff. Like, is it? Yeah, so got some catching up to do there, I think.
Right. Yes.
Dr. Sergey, it's the Sergey style.
Oh yeah, okay. Is that
Yeah.
just reverse flipped like composition or?
Yeah, it is reverse composition. Now, some papers use semicolon for composition.
Okay, yeah.
In the forward facing. Forward. Right, which is the first you apply the first function, and then you get the result. Then you apply the second function to that result.
Yeah.
Now, that is not the usual circle composition, which is backward.
I see. Okay.
Now, I did see some papers that used the semicolon to denote the forward composition, and then I decided that the usual semicolon is somehow confusing, and so because the usual semicolon is used in just as punctuation for no particular reason, right? So then I decided, well, this dot. Some people use a dot instead of a circle, right? Which is so then I decided, why don't I inflate the semicolon?
Yeah.
Like the dot is inflated and becomes a little circle.
Yeah.
And so I inflate the entire semicolon. And luckily there was a symbol already of this inflated semicolon. And so then I decided to use that symbol. So this is just now, I feel that the forward composition is somewhat easier to use in reasoning, in proofs.
Yeah.
So it is not, maybe not very well. And actually in some programming languages, there is a similar operation, which I also use, the triangle, the forward-looking triangle.
Yeah.
Which is used in some languages.
Yeah, like Elm, I'm used to seeing that.
Right now, in Scala, you do not need that most of the time, because you have the dot method notation, the dot method syntax. But in order to faithfully reproduce the dot method syntax, you really need this forward triangle, because the dot method has the argument on the left and the function on the right. And then you chain them, and again the argument is on the left, right? So that is the kind of motivation that I had in order to make proofs easier. Also, if you look at the commutative diagram for the type diagram, you have types connected with arrows. It's much easier to read that if you have forward composition, right? You have the first function and the second function, and then you can kind of follow the types in your head more easily. That's what I found. Now that's, other than that, and also there is a matrix notation. Now the matrix notation maybe is going to frighten away a lot of people. The matrix notation is certainly something that I haven't seen in other papers. I decided to use it. Now, the matrix notation is adapted to the forward composition and to the triangle. If you wanted to use the backward composition and the dollar instead of a triangle, so Haskell dollar, right?
Yeah.
Then you would have to change the matrix notation, because that the usual matrix multiplication rule needs to be transposed. So you have to transpose all matrices essentially. And when you transpose matrices, the order of composition also reverses. So you have to do that. So you can take all proofs and mechanically reverse everything, and put dollar signs instead of triangles, and circles instead of semicolons, and transpose all matrices and reverse the order of their composition. And then all proofs will be still valid just because it's a syntax. There's no difference really between that and that. But I just feel that it is easier to reason like that.
Mhm. Nice. Yeah, thanks for the explanation. Yeah.
Now, another thing that that should scare people away from my book is that I have a lot of derivations, a lot of calculations and proofs. So, I mean, people are certainly not used to that in the programming community, because people in the programming community are not engineers. They don't study like formal mathematics before they start working. Right? They study syntax of some programming languages and then they start writing code. So people are not used to having a lot of formulas in a book. But precisely because there isn't any book of that kind, I'm writing it. There are all kinds of other books that explain functional programming in detail without even saying the word monad even once.
Yeah.
Right? So there are all those books that explain in all kinds of ways, without any formulas, without any proofs, without any derivations, without even saying that there are laws for any of this.
Yeah.
Right? There are already plenty of those books, and I'm not going to write another one. And so, anyway, I feel that there is no book that goes in depth to prove, for instance, that certain monads are correct. You know, I don't know. So I don't know what your background is. I just joined, so you were doing your intro. But if you have if you have looked at some monad code, then it's not always clear what it even does and why it's like that. And so, you know, you can look at the library implementing different monads. You would never get even an idea of why that is there. What are these things? You know, why do you need them, and why is the code like this, and what it is doing? So unless you understand the laws behind it and you have a lot of examples, and you generalize from those examples, and you understand that there's a law, and you generalize from the laws, you understand that there are classes of laws, and there's a system behind it. It's not just, you know, laws that come from the sky and because somebody decided to have them. No, there's a system actually. Then you start looking into category theory and understand that there is a kind of generalization behind all of it that is even higher than specific type classes. And then, so that's what it is. And so you have to go through that in this. So that's what my book is about. So starting from practical needs, like what data types have the monad instance, what data types have the functor instance, are they correct? You know, they show me, there is a book that's called the Book of Monads, and it's full of monads. But there isn't a single proof in that book that the laws, not a single one, not a single monad is justified, that the code is correct. And sometimes you can have different implementations of the same type signal. You need to justify that implementation is correct.
Yep. That
is not done. There isn't a single book that gives a proof for the state monad. So anyway, that is the omission that I found in current functional programming literature.
Makes sense. Yeah. I'm definitely pretty motivated by the math side of it too. I think, I kind of came into functional programming through Haskell, and I guess like Haskell from first principles, read through all of that, and then just got interested in the category theory. So just watched a lot of Bartosz Milewski videos and stuff like that. So less knowledgeable actually about some of the practical applications that I haven't been Scala in a few years. So I actually don't remember a lot of the syntax there I do a little more Haskell for hobby stuff. But,
Yeah. You see. Well,
Yeah.
that's cool. Welcome. In any
Thank you.
case, I hope you enjoyed.
Hi, Matt. I'm Hugh. Just briefly, I got my math PhD. I liked categories. I did them sort of for fun. It was not my main thing. And now I'm a programmer who knows more math than is usual. And, I do functional languages for fun as a kind of diversion from my everyday job. So anyway, I'm just kind of curious about this stuff in general.
Nice to meet you.
So I guess as long as we're doing the intro thing, I'm Adrian, and I actually founded this meetup group about 10, 12 years ago, mainly because I was interested in dependently typed languages and the very high degree of expressiveness that they provide. And so that has led me to look at not just how you prove stuff in a dependently typed language, but what sorts of things you would want to prove things about, which include, of course, all of the standard structures that you use in programming languages, like all the stuff in Sergey's book. And so Sergey has very helpfully outlined all of the proofs that you would do if you were writing a library for a dependently typed language to show that these structures are well behaved.
Right.
And
Well,
I'm Pete Vanderbilt, and I've been a member of this group for a pretty long time. And like Adrian, I'm interested in dependently typed languages, and I'm playing around with designing one that has more object-oriented feel to it. Most dependently typed languages are more based on, having, plain data structures and then all the operations on the outside that operate on them. Whereas objects more like you have the data structure, but the operations are sort of associated with it directly. And you can get dynamic dispatch and things like that. So I'm trying to bring the functional concepts into that sort of language.
Pretty cool. Yeah.
Hey, I'm Wayne. I am actually from a Harvard background, computer architecture kind of thing. And then I mostly work in the semiconductor industry. But over time, I kind of could draw more into the software and math side. And then I kind of enjoyed joining this group discussion and then kind of learn more of having more of a solid foundation on the math and theory, and rather than just being an engineer and then rely on heuristics and experience. So that's why I'm here.
Nice. Good. Sweet.
Okay.
I
So,
introduce myself as well.
oh, you should. Yes, of course. The author.
Thank you.
Oh.
Yeah, well, I don't want to be just limited to being an author of this book. This book is kind of an outgrowth of what I've been doing for the last 10 years, which is playing around with functional programming. Eventually, I got a job in Scala, which certainly helped, but it does not satisfy my curiosity enough. I've been with this meetup also quite a while, and I have a background of theoretical physics, which I abandoned about 13 years ago. But certainly I'm very, very familiar and kind of used to having a lot of calculations and a lot of formulas. Like mathematicians, I believe, are more averse to long calculations than physicists. So mathematicians would like to say it's obvious because of some cute trick or something. And
Yeah.
physicists would just say, well, let's compute it in a straightforward way, substitute everything until 0 equals 0. And so anyway, so that is kind of my approach. I'm not shy of long calculations if they're necessary. I'm happy to make them shorter. But for also, I'm interested in dependent type languages, but only from a very narrow perspective. I'd like to understand how they can improve my life as a programmer. I'm not so much interested in, how much elegance you can get, or can you prove automatically the Fermat theorem or something like this. I'm less interested in that, but certainly if there is some development in that direction that makes my life easier, that I'll be very interested in doing that. So if somebody designs a new dependently typed language where my web server will have fewer mistakes, and my database will, when the connection to the database crashes, I don't forget to refresh it. That kind of thing. If I can get that, then I'm very interested.
I also have a physics background, so that's my start.
Right.
Yeah, no, I'm just doing software engineering.
Right. Yeah. All right. Well, thank you. Andreas is. I'm not sure if Andreas can hear us. All right.
So I had some stuff left over from last time. If I can take over for a moment.
Okay.
So if you will recall, last time I had started, whoops, that is the wrong window. I have the right window here somewhere, I think. Maybe I don't. Give me a second. Yeah, I had started to do something in Agda, trying to do some proofs about filterable, and I had not gotten very far, and I said that I would get farther for this meeting, but then I immediately got stuck. And so the place where I got stuck was as soon as you try to talk about deflate and you want to use get from the maybe version for get. Get is a partial function. And Agda doesn't do partial functions, at least not in the same way that that Scala does. You can't throw an exception. So the normal way to do a get on a maybe would be to return a maybe. That is, it would be the identity function. And so I thought, well, the alternate set of laws for filter, the ones that depend on deflate, maybe those just can't be expressed in a total language. And then it was only this morning that I realized, well, actually, you can deal with partial functions in Agda. All you have to do is have some extra information to prove that they are not partial.
Right.
And so, for example, you can do a version of get like this, where you have a maybe, but you also have a proof that the maybe isn't empty. And then as long as you have that, then you can get the thing out of your maybe.
Can you explain this? So why is it x supposed to be equal to a function from nothing to
So
nothing?
No.
the parentheses are like this,
Uh,
right? So what I'm
I
saying,
see. I see. I
right?
see. Good,
X
thank
X
you,
isn't
thank you.
empty.
Right. Right. Thank you.
So
Oh, is that okay?
Yeah.
Is that a not equal or
No,
Yeah,
is
that's-
there a
it's
symbol
equal.
for the?
No,
There
that's
is a
just the
symbol.
cursor. That's the mouse. That's the mouse.
Oh, it's the cursor. Okay.
right.
Move the mouse away or something.
If you're asking, does
Yeah.
Agda have a symbol for not equal? I'm pretty sure it does. I'm pretty sure it expands to this, but that would require figuring out how to type it in Unicode, and that was an adventure that I didn't embark on.
Right.
So
Well,
this says that if x is nothing, then like the world ends, right? Then
Yep.
false.
Right.
False.
Okay.
Right. So that means
essentially, you can prove whatever you want in that case.
Right. And then everything is true.
Yeah.
Right.
Everything is true.
and so
Yeah.
Whatever
Right.
you wanted to get, you get. So yeah, but that's correct. So you're only supposed to apply get to after filtering.
yes.
So after filtering, then the filter function should produce a proof that its values are satisfying the predicate or something. And then there's not
Yeah.
going to be
Right.
nothing.
But yeah, that's where I get stuck now,
Uh-huh.
because filter like fmap, it's it doesn't reveal a whole lot of information. It doesn't, in particular, it doesn't let you do a fold, which would kind of give you a summary of the data structure that you had gone over. And a fold could tell you, oh yes, there are no empty elements in here.
That's not what you want. You want this proof separately with every element. You don't
Or you
a
want
summary.
P to be a type of a proof of some proposition.
What I'm going to want is a proof that for all VAs that are in the filtered data structure, X isn't nothing now. Would it be like that? No.
One way to get there is go up to that triple equals, put your cursor there and then type option dot or
Okay.
whatever it is. Okay. And then
Right.
you could probably see the other version. No.
Yeah, this declaration only has doesn't have the negative one. So
Okay. Well, yeah.
So what if you modify filter so that it returns not the data, so it returns a data structure containing pairs of X and the proof that X satisfies the predicate or something like this. Or if you are already at the level of maybe, then you can have a function that filters into maybe, together with a proof that those maybes are not empty somehow.
right. So, but I'm not sure how to express that without making more assumptions than filter makes.
I don't think filter makes more assumptions. How do you, why? Filter does, so suppose you have a list, and you filter on a list, right?
Mm-hmm.
The result of filtering is another list of the same type.
Right.
So why don't we change that? And instead we'll have a result, which is a list of pairs of a value of this type and the proof that the predicate was true on this value.
Yeah, you could do.
So we just modify the filter's type signature, and this proof you will then use later, right? When you want to prove that filter is equivalent to deflate, or if you want to derive deflate from filter, then you use that proof, and then in deflate you won't have this proof anymore.
Right. So, but that seems contrary to the whole spirit of the thing, which is that we want to use filter's original interface.
No,
So
I don't believe that this is a problem. No. I don't think you can, because you see, you cannot just say I have a list of X and then separately a list of proofs. That won't do, because you cannot zip these together.
Right.
In general.
Yeah.
Right?
Yes. You have to associate the proof with each element.
Yeah. So I don't. And okay. Well, let me just explain my intuition. Is that in a non-dependently typed language, all this information is kind of implicit in there. You know, you have filtered, and then you apply a partial function. Why is it safe? Well, you know it is safe. It's implicitly in your head that it is safe to apply, but actually it is not safe in general. And so this proof that it is safe is implicit in the assumption that the partial function law holds. Now, it is in Agda, you have to put this assumption directly into the type. In Scala, you don't, because there's no reasonable way of doing that. I believe that Scala can do a lot of dependently typed stuff, but in just a very ugly and unusable way.
Yes,
So,
it's so verbose that when I've seen people express some pretty sophisticated dependent types in Scala, but it takes so much text that I can't follow it.
It's not useful then. It's not useful for practice. You have to make it so that it's not so verbose, and that it's clear what you're doing. In Agda already it's very hard. Anyway, so my intuition would be it's fine to modify your type signature, because you can prove more, and then you can always discard the proof term.
Right.
At the end.
I think
so. I have another approach.
Okay.
I mean, all you really want to know is that that predicate is true of the elements, and usually that proof is just REFL. So it's not all that useful to keep it around. Another option is to basically have filter return the list and basically return another assertion that if you were to F-map P over the list, it would be universally true. So that you can always kind of go back and say, oh, if I need that P is true of this, I can just get it. But this is what, more like what Sergey was saying.
Right. So
you're just writing down a free applicative in there. you're writing a zip operation. You're telling me that I can do the zip operation later and get the proof term for anything I want. Whatever is easier. If this is easy to the safe filter, if this is easy to deal with and prove things about, then good. If what Peter is saying is that you return f of x, and then you also return a function from that value, from that f of x, and to something, right? How do you do that?
Yes, I'm not quite following that.
Well, let's go ahead with this one, I guess.
Right. With this approach, I think you can derive regular filter from safe filter. So if safe filter is your primitive, then you can probably You can get a lot farther.
I would
Because you could
suggest
just record.
you can always drop that proof term later. As you have an F map now. What would be interesting, of course, is if you had a contravariant functor. When F is contravariant, then it's not obvious what to do, because you cannot just drop things. You don't have F map on the contravariant type constructor. You have C map instead. So anyway, but let's just forget about that for now.
Right.
Because deflate is also different for contravariant. It's not, there's no deflate. There's something else instead. There's inflate. So yeah, you just won't be doing the same proofs for the contravariant. So let's just forget about contravariant for now. If you, I'm pretty sure if you can figure out covariant, then it will be easy to do the contravariant version.
Right, I would think so. You just co it.
No, you contra it.
Contra it, whatever. Yes. So, so that was one of the directions I was heading that I didn't get very far in. So there's the other question that we had last time, which is whether there are filterables where you can say that you don't throw out anything that you don't have to throw out. I think you could call them conservative filterables, meaning that for every element for which the filtering function returns true, you retain it, whatever retaining it means. So we had the example of the tree and a non-conservative filter that rejects a node in the tree can throw out the entire subtree. But a conservative filter on a tree would have to rebuild the tree with all of the nodes that pass the filter still in the tree. And so I was trying to think about, well, how would you express the laws of a conservative filter? First of all, does anybody care whether a filter is conservative or not? That I'm not sure about. But I think for a lot of data structures like lists, people's intuition is that filter will be conservative. It's not going to throw away any element of the list that for which the filter returns true. So, so what I was wondering, because we have laws that are expressed in terms of ID, are there laws about ID? That is, can we say that if we have a decidable equality on the type of X, can we say that ID of X equals X? Where equals is the decidable equality. And I would think we might be able to say that. Certainly in Scala, we can, where we have a propositional equality, we can say that. Or sorry, not Scala, I mean Agda.
So why is it important to consider this ID business?
Well,
just want to compare what was before and what was after the filter.
Yes.
Equality in them.
Yes. So
I would first ask a more basic question. Are you talking about polynomial functors? Maybe only. Maybe are you talking about traversable functors that you can fold over, that you can talk? So see, the intuition is that the data structure contains values, contains 0 or more values and you can iterate over them and see what they are. Because not all filterables are like that.
Right.
So sometimes you cannot iterate over what is in there because there are just
Right.
too many of those things in there. But you can still filter. So
Yeah.
so if you can say that this is only for traversables, which is the same as polynomial essentially. So you do not allow any function errors in the type of the functor. Then maybe you just say, yes, this needs to be a traversable, so or a foldable, whatever if you like, so that you can fold over it, and then you can maybe formulate a law that says that folding after filter and folding before filter must be related in some way. So first you fold, and then let's say you count the number of elements or something that satisfies some condition. And then you first filter, and then you again count the number of elements that satisfy this condition. And that must be the same. Of course, you don't want to just talk about count. You want to express this in terms of arbitrary effect on a fold, so which is a traversal. So if you fold with effect, and then you say that something, I don't know how, but you can probably talk about it in this way. Because before you have anything to compare, you need to understand how to get those values out, to compare them. And foldable essentially is the same as being able to convert your data structure to a sequence.
Right.
So if you can convert your data structure to a sequence, to a finite sequence, then you can talk about elements in the sequence, and then you can just try to formulate your law. But if you don't first impose that constraint that your data structure must be foldable, then I don't know how you can formulate a law.
Right. So that's why I was trying to think about the law not in terms of foldable, but in terms of equalities. So the fact that we use an ID here, at least in this one law, that suggests to me that we have some way of comparing, or at least proving, that the application of these two functions, namely a filter that always returns true and ID, that the results of those will be equal somehow. And that suggests that we have a way of talking about filterable structures that are not equal. So if, for example, you had a filter, not necessarily one that always returns true, but a filter such that it did not modify a particular data structure when you applied it, then you would have some intuition, at least, that the filter function never returns false for any of the things that are in the structure. And so then maybe you could start to phrase the question about, well, what is in this structure in terms of single element filters? So suppose that you have a filter that will return false only for one particular element of the data type. Then you could test whether or not a filterable had that element in it by filtering on it and seeing whether it was the same or not. If the input is the same as the output, then it didn't have the element that would be removed. So, but I don't know if that's a legitimate line of reasoning. I it certainly would help to have a decidable equality on both the element type and the filterable type. But then maybe that's equivalent to having a traversable. So
well, I can comment and say that first of all, it is perhaps a problem in my book that I don't talk about how this equality is defined. So the identity law filter is supposed to verify that the data structure remains the same, right? But how can we verify that if this data structure is a function?
yes.
Right? If it is not some kind of polynomial data structure that you can just compare element by element and eventually the comparison stops. But it's a function or even a higher order function, right? Where you cannot possibly enumerate all values or anything that's in there. You don't know how to do that. There's no way of doing that.
Right.
In that case, it is not clear what it means that they're equal. So how do you verify that this law? So essentially, it's how do you call it? Definitional? No.
It's a propositional equality.
Propositional equality, right? So
right.
You have to demonstrate propositional equality.
Yes.
Otherwise, there's no way. I have examples of filterable functors that are not polynomial. You can take any covariant functor. I think I said that in the slide last time. Right? You can take any covariant functor, f of a, and instead of f of a, you write f of 1 plus a. And that becomes filterable. It's a free filterable on the functor. And so if f is an arbitrary higher order function, as long as it's covariant in a, right? It doesn't have to be strictly positive. It can be positive, but not strictly positive. So it can have arbitrarily complicated structure in terms of higher order functions. And it's totally unclear how you would talk about values stored in that structure. So, however, you can certainly demonstrate a propositional equality after the true filter.
Right.
Now, if you say now, is this filter conservative? Now, it's not so easy to understand that question. So, how do you talk about values that are stored in that structure? What are those values that are stored in it?
Right.
Right? So you have a higher order function that does not necessarily deliver values of type A, right? Even if you apply it to some arguments, right? It doesn't have to deliver values of type A. So what does it mean that it stores values of type A? It actually maybe doesn't, or maybe it does in some strange way, which you cannot extract from that data structure, and you cannot check if one of them is in there or not. It's just not clear to me how you would talk about that. So maybe you have to restrict to traversable. That's my intention.
Right. Or you have to use a dependently typed language where you can use the appropriate methods for each function to prove the necessary propositional equality.
But I don't even know how to formulate it. So what they first said is that if the function returns, if the predicate returns true on every element, then the data structure remains unchanged. Okay, but that is essentially the same as the partial function. So if the filter is true, then you can apply a partial function that will not fail only when the predicate is true. So then you can talk about that. And now, if you now want, but this is the same in my view as the partial function law. So now you want to say you apply a filter with a predicate that fails on some values that are contained in the data structure. How do you define that? If you don't know what values are in there, there's no way of extracting values, and there's no way of putting them in either necessarily.
Right.
So I don't know. So do you have a
but if you can prove propositionally that a filtered data structure is different after you filter, then that at least says something about the relationship between the filter and the elements in the data structure.
Can you say something that the partial function actually failed? That you applied. So suppose you apply a fmap with a partial function to this data structure. Can you? So the partial function law says that you can do that after a filter, and then everything is fine. But what if you don't filter? You apply the partial function to a data structure that contained the wrong values. Can you reason about the result of that? Can you say, oh, that actually blew up, and now I can prove that it blew up?
You never call it.
Right. You can't write a function that doesn't handle all cases in Octa. So you can't prove anything about such a function because no such function exists. But you can write a function that returns A or nothing if you have information that it will never actually return nothing.
Okay. So suppose you had a list of 3 elements, and you apply a fmap on it with a partial function, which returns this A or nothing, A or bottom.
Yes.
And then one of the elements doesn't satisfy the condition, and then can you prove that then it returns bottom?
The compiler will not let you get to the point where you can filter with that, because you have to have the proof ahead of time that you will not blow up.
Or can you prove that if you wanted to prove it, you would fail? Is there any way of reasoning?
You could return an option.
Right. You would have to return. Yeah, you would have to rephrase your partial function as a maybe, as an option. So can I actually do? No. Backslash E1. Oh, yes, there's a hollow 1. Ha! Who knew?
I had a quick question. What would a filterable instance look like for a function? It sounded like you were alluding to the fact that it's not, you can define filterable instances for things that are not foldable. But wouldn't that be a partial function, or?
No, it's so you can define a filterable instance for a number of functors that are not polynomial, not foldable. And now, how you define? Well, you just write code that kind of does what you need. And you will find, for example, maybe you need an example of that. So an example is, let's consider the continuation monad, right? right? So it's a function from A to R to R, right? Now, instead of A, let's take maybe A. So that's going to be 1 plus R to R to R, 1 plus A to R to R.
Mhm.
So that is a filterable functor. Because what you can do is so it has this 1 plus A in there, and so that means that the argument of the continuation is a function that is required to be able to ignore the argument A if necessary.
Right. Yep.
So then you apply the filter to this argument of type A, and if the predicate passes, then you pass the A, and if the predicate fails, then you ignore that A and put a nothing in that function. So you kind of modify the argument of that function before you call it, and then you give that modified function to the continuation value as a continuation, and that's how you filter. And so then you're guaranteed that invalid values on which predicate does not hold will never be arguments of this function. And that is what filterable wants. It wants to exclude values. Now, if these values are inside a higher order function, if they are arguments of a function, then they need to be excluded. This function may never be called over. So that's how it works. So you can write it down, and then all the laws are satisfied. Now the continuation is certainly not the same. So the value of type function of maybe A to R is certainly not the same as having some values of type A. And you cannot extract from it values of type A. And you cannot say how many there are. These questions cannot be answered. So there's no function from a continuation type to A, for example, right? That cannot be implemented. So that's an example. It's kind of a simplest example where you have a non-polynomial functor that is filterable, for which a lot of the intuitions that we have just don't work. It's not a data structure that has a container-like behavior, which is one, zero or more distinct values that you can talk about or iterate over. You cannot iterate over anything in there. But you can do fmap. And when you do fmap on this, you can do an fmap with a partial function. And if that partial function ever encounters an invalid value, it will blow up. So I'm trying to get at this part of the reasoning. Can I say my continuation monad thing contains a value x if I fmap it with a partial function that will fail at x and the result blows up? That is my definition of what it means that this thing contains a value x. Now see what I mean. So I'm taking liberty of drawing on top of the screen for a short time.
I
see
can.
it. Oh, there it is.
Mhm.
Right. So this is f of a. It's going to be this.
Oh yeah. So the A actually, it is actually functorial in A because it's like a double negative. I was confused
Correct.
about it being on the left of the arrow. So
That's right. That's correct. Yeah.
Okay. I see.
Right.
Yeah.
So it is a covariant functor. It is, however, it is filterable. So you can implement, for example, you can easily implement deflate. Right? Deflate f of 1 plus a going to f of a. It's very easy because f of 1 plus a is just you have 1 plus 1 plus a going to r to r. So you can collapse that. It's a flattening. It's a monad join operation on that. Right? So it's 1 plus 1 plus a going to R, going
Yep.
to R, right? You can just easily collapse this 1 plus 1 plus A going to 1 plus A.
Yep.
And then you're done. So you can very easily implement deflate. And by just looking at this, you can see this works for any functor f. So that's why this construction f of 1 plus A is a universal kind of construction that makes a filterable functor out of anything, out of any functor. Anyway, that's all I wanted to say. So this is an example that you want to keep in mind. So if you can somehow formulate a law that says, I have a partial function that fails on a certain value of x, and then the filter of the particular value will fail also. It will also somehow fail, whatever that means, I don't know, because you say that Agda doesn't like bottom and doesn't like you, because in Scala you would say, oh, it just throws an exception. It throws an exception. But that is, of course, not the same as having a proof. So maybe you can formulate somehow that for that property that you need to maybe modify again the filter type signature, or I don't know what you want to do, but
Right. I'm thinking that if you start with this safe filter idea, that you may be able to derive all of the desirable properties of filter.
I mean, you're trying to introduce one more property, right? Conservative filter.
Well,
I'm trying to understand how even to formulate that without I mean, traversable is quite ugly. You kind of completely throw away all the data structure, you replace it with a list, and then you are quite inelegantly talking about list.
Right. So there are two sort of big questions that I have, and one of them is about sort of alternate phrasings of filter in general. If the formulation with deflate doesn't work because get is partial, what else can you use? And so that's sort of answered by save filter. And then there's this whole other question about what does it mean for a filter to be conservative? And there I have less intuition about how to proceed. Although maybe if you start with safe filter and you have this proof that something is true for an element, maybe there's a way to filter on the result of this and manipulate the Booleans explicitly. I don't know. I will have to wait for inspiration if I.
Well, the thing is, you look at the type signature of safe filter. The result is a f of something.
Yes.
Right. So you don't know what's in it. You cannot say that something is in it. You have to f map over it.
Yes, you can't say that something is in it, but you can say everything that is in it has this property, that the filter function return true.
Yes. Well, whatever is in it, once you f map over this, then
Yes.
The function that you f map with will have that as an argument.
Yes.
Now, but what if f becomes empty after filter, completely empty? Then you can formulate as many laws as you want; they will all be true for an empty set.
Yes. As long as they quantify over the empty thing, yes, anything can be true.
Right. So, I mean, you can also, another example that you can keep in mind is a kind of overly greedy non-conservative filter, which is that if the predicate fails for even one element in the list, then the entire result is an empty list,
Yes.
right? So that is fine. That is still satisfies the laws. You want to, so how would you formulate a law? You know, it will still be the safe filter type signature. The safe filter type signature will be still there,
Right.
right?
yes,
There just won't be any elements in there, but you won't know. So
Yes.
so how do you formulate the law? I don't
Right.
know. I'm just
I
saying,
don't-
well, unless you somehow have a partial function and you can formulate the restriction that fmap with that partial function must fail,
Mhm.
right? I don't know how we do that.
Yes, I don't know either.
It's a very interesting question, and actually,
Yeah.
yeah, it's actually a hidden kind of a hidden detail that you need to be able to compare functions, which you're not supposed to do usually,
Yes.
in order
Yeah,
to
yeah.
even formulate this law.
Right. You don't necessarily have to have a decidable equality, I don't think, but you have to have some notion of whether functions are equal. So,
Right.
Random other thought of looking
Yeah.
at the composition law for the filter. It seems like if you, and that has a conjunction in it. Is there a way to define a law with a disjunction? I mean, that would also, yeah, require more to. I mean, it seems like something like that might be able to express this conservative or non-conservative idea, like filtering, splitting up the structure in two different ways and filtering and then sticking them back together should be the same as, yeah, it's like a vague idea. I don't know if that makes any sense, but
yeah, yeah, that might be.
I
an
was wondering
interesting-
about, but I was thinking about that very briefly, but I couldn't see what to replace the function composition with on the left side of that.
Mhm.
I agree that intuitively, if we take the disjunction of two predicates, there are things we should probably expect about the result. But I don't know how to say that offhand.
Right. I mean, if you're taking the disjunction of two predicates, the filtered thing should be, I guess, at least as big as if you take the conjunction. But I don't know how to say at least as big.
right.
Or at least as big as if you take either predicate separately.
Right.
So let's take this continuation example. Can you formulate that? Can you say that it's at least as big? It's kind of infinitely big already.
Yes, I don't think I can say that.
I just wanted to say I would need to drop off in about 10 minutes or so, maybe. I will have to go, but anyway, you can. I'll leave it on.
Okay, well then maybe now is a good time to bring up something slightly different. Pete is wondering.
Can I just show, I did a quick AGDA of different, things that we were talking about. Let me just show this quickly, if you don't mind.
Now let me unshare.
Okay. Actually, I just need this window. So so these are a bunch of type definitions. So say filter 0 is just sort of the usual one where we basically take a f of a and a predicate and return an f of a. And then this first one is, I'm just cheating a little bit because I don't have functor here, so I'm just saying implicitly take a set to set thing and then an F map, you know, so that's just an argument. And I don't actually use it, but so the second one basically says we take, you know, the list and the predicate and we return F of a pair consisting of an A and then a proof, you know, that P of A is true. So in that case, we'd be returning pairs of A and the proof.
Right. So
and then
that's my
this
safe filter.
right.
Yeah.
And then
Okay.
this safe filter 2 is sort of the one I was suggesting earlier, where what we do is we return the whole list, F of A or whatever it is, and then we return basically a proof that every application of P to X is true. And I just cheated there and just said, okay, well, I'm taking in a function all that computes, that basically does that.
Right. So
So
it's all equivalent to something like a traversable or a foldable.
Foldable,
I
traversable, whatever. I mean, the thing is,
I don't-
foldable and
yeah.
traversable already forces you to have polynomial. So, but anyway, okay.
all would be a foldable, if that's what you're asking. All is probably going to be implemented in terms of fold. But I'm not sure what you're asking.
I'm asking, would the continuation type that I was writing before fit this type signature? So can you implement the function all for that type? See what I mean? So you have, because that's kind of a simplest example of filterable that is not traversable, not foldable, and not traversable. So can you implement a function of this type signature, all, which is a to bool, and then this horrible continuation thing, and then bool.
I don't know. I'd have to look at it in more detail.
Because I mean, I'm just curious, because intuitively this looks like you need to fold over it, but and certainly you can implement it always returning true if that's what you feel like, but that's not what you want.
Well, maybe I'll work on that. Where's the continuation in your?
It's something I just scribbled on the screen right now.
Oh, okay.
I don't think I have that explicitly as an example. I think I have some examples like that somewhere. But certainly I did not write it down. If you want, I can write it down again. Essentially, it's a maybe to R to R, maybe A to R to R. The simplest. I think. Well, it's just that you can have also a contravariant filterables, which will all be functions. You can have different things that are filterable, that are not strictly positive, and then I don't know what to do. But yeah. I mean, there's another example. Let's see. Whiteboard. Okay, whiteboard. Get rid of this. F of A. So first example is 1 plus A to R to R. Second example is A to 1 plus R to R. Because in this case, if A fails, then you can always return 1. instead of returning a value of type R. So you can modify this function so that it never has to be applied to invalid values. The intuition for contravariant filterable is that it's a function that consumes values of type A. And if you can filter it, it means you can modify that function so that it never has to consume invalid values of type A. So these types allow this kind of modification. So, but anyway, the F defined here, they're covariant in A, and they're filterable, but there's no clearly defined notion of all values contained in F satisfy a certain property.
Right.
You can
Here's
define
where you-
that by saying that you don't know what, if you define what you defined accords to your intuition.
Right. Here's where I think you can use the idea that if something was filtered out, then the result is different.
Right.
Because if
But actually the result will always be different. Because you see this function, this function here is going to be modified by the filter, so that it never applies to function to values of where the predicate is not satisfied. So this function is always going to be modified. There's
well,
no,
if you filter with a filter that always returns true,
yeah, then it's not
then-
modified.
hmm,
Then it's not modified. That's right.
then it's not modified.
Yeah.
Yes.
But if you
So,
have a filter that doesn't always return true,
right,
then
because you could have any A, yes.
Yeah, you
So
could
it would
have
have to
any
be, yes.
there's no notion of the A's that are in there.
Yes.
In this sense, all A's are always
All
in there.
A's are in there, yes. I see.
So you satisfy the laws of filter as stated,
Mhm.
and then this is going to be non-conservative, if you wish, because all A's are always in there. So as long as you just invalidate a single A, you have changed this value.
Yes, but that's conservative as long as you don't invalidate other A's. That is,
Well, how do you mean other A's? So you have changed this value after filtering, right?
yes, if you filter on the non-always true filter, you will change the value. But the question is, I mean, you can measure conservativity incrementally. That is, if I apply a filter that filters out another value,
Mhm.
is it changed after that?
That's the composition law that already tells you
Yeah.
everything.
I don't think the composition law by itself tells us everything, because the filtering operation that throws out everything, if there's any if the filter ever returns false, is legal. So when you're talking about conservativity, though, conservativity is incremental. You're not allowed to throw out everything. Only the things for which the filter returns false.
Well, but you know what's going on, right? So if you apply the filter with some function, some predicate, you have changed the continuation value. If you apply again the same filter, you can prove that you have not changed that value. Yes, is that satisfying? I don't know.
Yeah. Yes. Well, it's certainly
The composition law tells you that it must be
composition.
like this.
Yes.
And so it is like this. It is
If
like
it's the
this.
same filter, yes, you
Same filter,
get the same thing.
The same thing. And so, yeah, okay, so the composition law already tells you that it must be like this. Does it satisfy your intuition for being conservative? I don't know.
Right. But again, the composition law doesn't tell me that I can't throw out everything. So what a conservativity law would say is, if you apply a filter that throws out some things, then any filter that returns false for additional things will then change the result. So if there are some values of A for which the first filter returned true and the second filter returns false, then the result after applying the first filter must be different from the result after applying the second one.
Right. Well, okay.
So
I would need to go, but
okay.
let me just say, maybe this continuation thing can be productively imagined as a collection that has all values of A at once, from which you can cross out arbitrarily some values, and then it becomes all values except those that you cross out. So maybe that's, I need to.
Okay. Well.
Please, yeah, recording will continue. I will notice.
So yeah, meanwhile, we did have, I guess, an administrative sort of thing. Pete was suggesting that we might want to work some additional material in while we are working through this book, because I think even though I find this material very interesting, it is very dense, and it might be nice to refresh ourselves by looking at related ideas, but from a different point of view. And Pete had a couple of papers that he thought would be interesting. And so I am wondering if we might want to do one of those for next time, and then perhaps pick up with the following chapter in this book. Pete, did you want to give a blurb for the papers you were proposing?
Yeah, let's see. Okay, give me a second here. Okay, one of the ones that I was interested in looking at is this one. Initial algebra semantics is enough. This is, basically talking about data types, and then how you can sort of like give a semantics to different data types in terms of initial algebras. And that's sort of a category theory concept that we looked at before. And this track is kind of category theory, or used to be. This paper kind of, to me, since I'm interested in languages and semantics of the languages, I like this whole initial algebra approach to things. And this is dealing with more like the more complex data structures, like for lambda calculus, where you have different forms of things. And she gets into, or they get into, how do you define F fold, which is sort of partially the initial, it's basically your core fold function. And then that fold is the way you sort of eliminate from a data type. And then build is the sort of opposite, where you're constructing a data type from stuff. And it gets into, some category theory stuff, and, then these higher order functors, and generalized fold build. And, basically the whole thing is that, that this initial algebra semantics can actually work on all these different things. It's a lot of hand waving because it's hard to kind of show you what's going on.
Mhm.
But it's a kind of, it uses a lot of Haskell, so it's kind of concrete. And I think you can go look at the library if you want to. So they're concretely defined higher order functor and that sort of thing. And then let's see, there were also some other papers that were related. Let's see if I still have that tab. Oh, maybe it's on my other computer. Okay, well, I don't have it right handy. I guess I should have been more prepared. Hang on
Yeah.
a sec.
That's okay. I mean, if
Yeah,
does anyone else would we be interested in looking at that paper? It seems to me that just by skimming it, we can see that it has some obvious connections to the category theory we were doing before, and also some connections to the way Sergey is looking at programming language structures. So it seems pretty apropos.
Sure, I'm game.
Yeah. So maybe,
Sure.
yeah, maybe do that paper for next time and then pick up on Sergey's chapter 10 after that. Okay, all right. At least we have a plan. So as far as the timing of the next meeting, I guess we might as well settle that while we're on the topic. Is 2 weeks from today good for everyone?
I think it works for me. We're talking the 22nd.
22nd, yes. So I will, that will be another of those weeks when I have a meeting immediately following this one, but the week before and the week after are even worse for me. So 22nd works.
The week after is worse for me too.
Yeah.
Probably the
can't-
22nd.
I can't do it. I'm going to be on vacation for a week, so
Oh,
you should probably just ignore me. Unless we have to move it
Move
way
it to
out.
the
I don't
6th.
think we should do that just for me.
yeah, we would have to move it to May 6th.
I could probably do that, but
Yeah.
again, that seems a little extreme. I'm happy just to catch up as best I can.
Okay, yeah, I mean, we'll try not to say anything completely original.
Yes. Don't do anything important while I'm away.
Okay. All right, so
Okay.
we have a plan, but meanwhile, we might want to go back and look at the further development section in chapter 9, because the Matt, you have missed some of the previous chapters, but Sergey likes to put all of the really strange and interesting stuff in the further developments section of each chapter. So you don't want to miss that.
Okay.
So in section 9.4.1, Sergey, let's see if I can. Does anybody have the book up so they can share the screen quickly? I can. But he has this table of forms of naturality laws, and I thought that was kind of interesting.
Oh, I lost you guys. Yeah, I have the book if you want me to show it.
Yeah, if you can. So I would have to go scrounge it. I usually look at the book on my other computer, which is behind me, and so I don't have it on this one.
Oops. Okay, what section? Oh,
9.4.1.
Further.
Yeah, this table with the naturality laws.
Yeah. Right. So so yeah, this first part, he's pulling different laws that he's already explained previously and showing their form and what they're operating on and saying, oh, a lot of these have common forms, and this table here kind of gives those forms. And Adrian, did you have something you wanted to say about that?
I don't know that I had any things specific to say about that, except that it was interesting to me that we can summarize all of these naturality laws in just 4 forms.
Right.
Yeah, this is
Yeah, I
supposed
looked
to
at
be,
this. Go ahead.
oh yeah, just curious, do you know if this is supposed to be exhaustive, like there's some proof of this argument for that, or it just collecting the things that have been seen so far? Or
I don't think it's meant to be exhaustive. Maybe, it handles all the ones in his book or something, but
Right.
I think he's observing that these 4 things capture a lot of the kinds of functors that you might be interested in operating on.
Right. They capture what we have
operate
done so
kinds
far.
of filters.
Yeah.
So he finds these naturality laws important when he's proving things, like the rule for filter or something like that, where, oops, guess I'm not being able to select stuff. Oops. Anyway, like this filter law here, it allows him to move the key part inside. And so he can kind of move things around by moving it over there. Then, this thing is by itself, and, then he can switch that around and stuff like that. So I think he finds these kinds of laws very useful for his proofs. And later on, I think he's sort of suggesting that maybe these, that maybe there's sort of a collection of proofs where you could sort of do it once at a higher level and then apply it to many different situations. As long as you're interested in proving things about your program. Because other than that, I'm not so sure how useful the naturality laws are to a programmer.
Right, that they're interested in, yeah, interesting to people who are proving stuff about these structures. So I guess a question I have is, will we find different type signatures in the future, in future chapters for which we will have different naturality laws? Or, yeah, will as Pete says, a generalized proof technique that covers all laws with a particular type signature, will that just carry us forward through the rest of the book? I don't know.
I know he's going to get into monads, and they're functors, but they have more stuff, and so I know there's laws there. And like this, the first law, the 8.8 law, I think that's kind of one of the laws that you get for monads. So things like that will carry forward, but then there'll be additional laws.
Right, but how many
Yeah.
different type signatures will those laws have? I guess.
Yeah, maybe they'll fit into this
Right, if they
structure.
fit into this box, then perhaps a lot of the work has already been done for us.
I see that
Yeah.
most of this appears to be from filter, right? Like about 2/3 of the examples here are from
Yeah,
filter.
filter seems to be a good deal more complicated than the other structures that we've looked at.
Yeah.
Yeah, I'd never seen this presentation of unfilterable functors before. Another, like a lot of the other stuff is more familiar.
Yeah, I think, Sergey kind of observed that, a lot of books talk about all, other kinds of functors and operations on them, FMAP and stuff like that. But nobody really talked about the laws for filter. So that's part of his contribution to the world, I guess. It's the laws for filterable functors. So that's why we get this whole chapter is kind of on that. And but I think maybe as we get to later chapters, it won't all be about filterable functors. It'll be about other kinds, and hopefully there'll be laws for those that fit this framework.
Can somebody remind me what the meaning of the function f and then to the up arrow capital F means, as opposed to
That's F.
down arrow?
Well, they're both FMAP. Well, up arrow F is like for a covariant functor, it's FMAP.
Right.
And the down arrow is for a contravariant functor, it's CMAP or whatever the contramap,
So F, little f, up arrow, big F, I think would conventionally be written big F parentheses little
F of F.
Yes. Mm-hmm.
In category theory, definitely, that's very common.
Okay, I got it. Yeah, as opposed to, because without the up arrow, it means you apply F as an argument to the small f, right? In his notation. So,
yeah. Right. So where there's like small t up, and then a superscript of big A, that's basically we're saying we're applying t to the type A in a sense, or t at type A, since these are polymorphic functions. And then if there's a superscript with a colon in it, like here, that's just declaring that G is a B to C function. So he uses the superscript for that too.
Right.
One of the things he points out for parameterized ones is that basically, where is it? You can define, you can basically turn them around. I don't know where it is now, but oh, where is it? Anyway, you basically can take one of these things and turn it around. You create a functor. Oh, here it is. You can create a functor H that's from basically C of A to G of A. And so you can basically, like, it's like currying, right? If we have a C of A to F of A to G of A, that's kind of like a function from C of A and, you know, cross F of A to G, and then you can flip them, or you can turn this into a functor that's from F of A to C of A to G of A. And he shows how to do that. And then your naturality laws just follow from, they're just the natural transformation laws applied to that modified functor, which I thought was kind of interesting. And,
I guess a general question I have is, if you're doing something like Haskell programming, do you often do these kind of transformations at the program level? In other words, you write, you know, some kind of a function that does something, and then you realize, oh, I can simplify this, or I can change things around by doing it, something like that. Is that often happening, or I'm just curious?
yeah, I'm not sure. I think Sergey has shown some examples. Well, this may be more like related to the Oneida lemma, but you know, where you have something complicated and then you use the Oneida lemma, and it's like, oh, I can make it be this much simpler thing. And you know, and he should, you know, that he does to sort of like actual code. And it's probably true of some of these laws too, that, you know, by maybe being able to switch things around, you can simplify the code or improve it.
Right. I mean, I think Haskell programmers, at least in my very limited experience with Haskell, you do sometimes realize that you're doing something and it has to be wrapped in some kind of more sophisticated structure. Like you are doing some fairly straightforward code, and then you realize, oh, I need some state here. I need to wrap this in the state monad or something like that. And in the other track, I expect we will see an example of that when Ben explains how to use generating functions in, or generating functors rather, in the definition of syntax trees. Because, you know, if you're defining a simple programming language, it's very easy to start out with what looks like a very simple data type that covers the possible forms of the terms in the language. But then you may need to do something at a higher level of abstraction and lift all of the stuff that you have been doing to this this to some functor or some monad or something. So, so I'm not sure that that is exactly the scenario that Young is thinking of, but I mean, there are times when you have to do sort of fancy transformations on your code.
Mhm.
So, yeah, so I guess the other sections here are the Kleisli section, Kleisli functions, and Kleisli composition.
Mhm.
And sort of a blurb on category theory, which I think
Yeah.
those of us who have been doing the category theory track are convinced that category theory can play a role here.
Right. So he defines, what a category is, and then sort of shows that in his world, there's, mainly these four kinds of categories, based on types. If you, the plain category just has functions from your objects are the types are types. So if you have A and B, morphisms between them are just regular functions from A to B. But if it's a reverse category, a dual kind of category, he calls it reverse, then the functions go the other way from object B to object A. Or you can have the Kleisli versions where you go from A to some functor M applied to B. It's actually probably a monad, that's why it's M. Or it can go the other direction, or you can have a category where the functions from object A to object B are from F of A to F of B. And then he kind of shows that by combining different versions of these things, we can get a lot of the different laws, because they're sort of, the functors act like, well, they're like categorical functors between two different categories, like a plain category and an Kleisli category. Because category, the composition, there's an identity law and a composition law that have to be true, and that's what a lot of its natural transformations depend on. That's just hand waving, but I think that's where he's going with this.
Right. Well, the book in theory is written for people who are not familiar with category theory at all, and so yeah,
Right.
This would be news to them, I suppose.
Right. And I guess partially it's about showing that the laws that you kind of get through category theory are equivalent to the laws that like he gave for filterable. Apparently they're equivalent, that the laws you would get through category theory and the laws that he gave, at the beginning of this section are equivalent. You can derive one from the other. So it kind of gives you a justification for why you might pick that particular set of laws versus some other set of laws, or leave one out or add an additional one, whatever.
Right.
Because like we were saying, it sort of seems like there should be a law that says you can't lose information. Your filter shouldn't lose information. But that's a different, that would be a different kind of filterable, I guess, and it would need an extra law, and it maybe doesn't follow from category theory. I don't know.
Right. So, Yes, I think the conservative filterable question is still open. But
Speaking of conserving information, I mean, there's a field called linear something that tries to, linear logic or something like that, that
mhm,
tries to define that you cannot just kind of, A does not imply A comma A because you have two occurrences of A. You can only
mhm.
have one, right? If you start out with one, then you can only have one. So I wonder if there's something, something like that, because it's kind of interesting. This was a long time ago when I was doing my graduate studies, but you can make a chip use arbitrarily small amount of energy, but only if the computation is reversible. In other words, if you do like a plus operation, then you lose information, then you have to dissipate energy. Whereas if you do a plus operation that keeps the sum and the, let's say, the difference, so that you can always get back to the beginning, then you can do it with arbitrarily small amount of energy. So anyways, I thought that was kind of interesting. Yeah.
Right. Yes, that is very interesting.
But it's kind of like by doing more work, you use less energy.
By conserving information, yes.
I
And so
see.
information loss has to dissipate as heat. And
Hmm.
most operations that we do, we lose information, right? 1 plus 2 becomes 3. So 3 has less information than 1 plus 2 as an expression. So anyways,
Hmm.
it's kind of like linear logic is representing some of that at the logic level. And I wonder too, if certain like filter, you lose information, I guess, more than map does, right? Because between if the map of F, if F itself is reversible, then map of F is reversible, right? So
Hmm.
Yeah,
anyways,
like map itself doesn't seem like it's losing energy. Maybe the function you're calling would lose energy, but if you
exactly.
applied map to the identity function, it wouldn't lose. It would lose
Exactly.
only a little bit of energy, right? So
Yeah.
Right.
you always have to lose some, I guess.
So then the question is, right, Matt notes the name for the principle is Landauer's principle. But yeah, I guess, is there a formulation of filter that doesn't throw stuff away? Like you filter out some things, but you keep them in another thing, and such that you can reverse your filter. I don't know if there is such a thing.
Closure has a
Well,
function called partition, which given a list will partition it into those that satisfy the predicate and those that don't. So I
Right.
wonder if,
Yeah.
that sometimes can be useful, but yeah.
Right. Does every filterable imply a partition? Maybe is there a way to phrase filter in terms of partition such that we can express conservativity in terms of partition? I don't know.
And you still lose information with partition, right? Because you couldn't take the two partitions and get back to the original thing without knowing what the shuffle order was, or yeah.
Right.
Yeah.
Unless you started out with a set where the order is immaterial, but yeah, you're right. If there is an ordering, then getting back to the original, yeah.
Right. Maybe there's a sort of partition plus where you get the two pieces plus some information on how to reassemble them into the original.
Exactly.
well, it's this, yeah, it's almost like the sort of thing where you take the list and you basically, return the same list, but then you have the the value of the predicate on those things, you know, so you can look at all the true ones or you can look at all the false ones, you know exactly how to get the different lists out of that, but you haven't lost any information yet. And,
Right.
you know, the order's still there.
So is
So-
that the free filterable?
Ah. What would that mean exactly?
Well, I mean,
That's,
where you
that's-
keep the filterable thing plus a record of what the filter was, and then you don't really do anything with it,
hmm,
I guess. I don't know.
it's the sort of simplest thing you get if all you care about is your filter function and your thing, and there are no other laws involved. Or
Right.
something,
I mean that's how you do filterable on a stream, for example, because you can't go out if you have an infinite structure, you can't preemptively remove all of the stuff that you would remove. You have to do it lazily.
Mhm.
So, yeah, I have the feeling that unlike the other structures we have looked at in this book, there's more stuff to think about filter, and there's stuff that hasn't been figured out yet. Or I don't know.
Okay, well, we're almost out of time.
Yes, we are. So yeah, in a couple of weeks, shall we see whether initial algebras really are enough?
Sounds good.
Yeah, that'll be interesting. Because initial algebras have been around for decades, you know. When I was doing graduate studies, we were into initial algebra semantics. So yeah, I'm curious that there's still work being done on it.
Right. What is
Yeah.
the date of that paper?
You try to stick it on Slack. also?
2006, I think.
Ah,
What? Oh, sorry.
Sorry, can you try to stick it on Slack also? I guess
Yeah.
it will be in the meetup notes, but
right,
just
right.
in case.
Yes, I'll have the URL.
Yeah, I'll do that after this meeting.
Oh yeah, and what is the Slack channel? I'd like to join it. Is it just on the meetup or
I think I have to send you an invite.
okay. Yeah.
Can you send me a direct message on Meetup with your email address, and then I can send you the Slack channel invite?
Yes, I will do that. Yep. Thanks.
Okay, thanks. All right. I guess we've had enough fun for today then. So until next
All
time.
right.
All right. Yep. Nice to meet
Thank you.
everyone.
Okay.
Bye.
See you guys.
All right. Nice
Bye.
meeting you, man.
Bye.
Bye.